Great. Thanks everybody for tuning in today. This week, our seminar speaker is Dr. Sunanda Sharma, who is currently a postdoctoral researcher working at NASA's Jet Propulsion Laboratory. Dr. Sharma is an astrobiologist whose research mainly focuses on studying the limits of life and also thinking about detecting biosignatures and developing technology for that. They take an interdisciplinary approach. For example, they combine microscopy, spectroscopy, computational analyses, not only here on Earth, but also thinking about other planets, which she'll be sharing a little bit with us today. They received a bachelor's, master's, and PhD at MIT. After that, they did some consulting and some freelance. And then last year, they recently started their current postdoc position where they are supporting the SHERLOC instrument on the Mars 2020 Perseverance rover, which she'll be talking about today, I think. And so let's thank again Dr. Sharma for taking the time to talk with us. Take it away, it's all you. Thanks again.
Great, thank you so much for having me and thank you for the invitation. So yeah, I'm currently doing a postdoc at JPL. I work on the SHERLOC team with Dr. Luther Beagle as part of the Mars 2020 team. So my talk is searching for minerals and organics on Mars with SHERLOC. So this is a quick run through of what I'll go through. So this is a quick overview of astrobiology as related to this mission, what we're doing on Mars with the rover, and then zone in on the instrument that I work with, which is SHERLOC, and walk through some of the results that we have so far from the crater floor and other things that we hope to find during the mission. So starting with the first one, searching for habitable environments and signs of life. So, oops, all the arrows are here, but the rest of it isn't. So I first became interested in astrobiology very broadly during graduate school through the lens of microbiology. I was fascinated by the interactions between organisms and their environments, so local and global, and how those can mutually shape one another. And this led me to reading research on testing the limits of life in terms of where microbes can survive and the environments that they can survive or thrive in. And I worked with some model fungi like Aspergillus that are known to survive in high ionizing radiation environments. And so this is sort of the path I took towards astrobiology. And I'm still really fascinated by a lot of the different sides of the field. And in the context of astrobiology focused missions, there are two different sides that where I think that in situ exploration related to astrobiology can shine. So on one side, we have studies about origin-related things. So this is the search for potential building blocks of life, and on the other side we have traces. So first on one side, this is looking at what could be creating the building blocks of life, what are the elements that are there, and how do we detect them in different environments. And then those could potentially lead to the creation of things like organic molecules, which could then lead to the creation of cellular components, which could then exhibit functions like compartmentalization, replication, and metabolism, and could conceivably lead to a really early form of life. And this is kind of like how I learned that one side of origin of life in prebiotic chemistry. And like when you're going from not life to life, how does that transition happen? What are all the constituent components? And how do you go from just a collection of elements that exist in the solar system to something that does resemble life? So like that one direction is one side of where a lot of the instrumentation that I'm going to talk about can be useful. The other side is the one that I think we talk about more in the context of the mission, which is searching for traces of life that did exist in an environment by searching for biosignatures following some definitions of biosignatures. So say you actually start with life rather than starting with all of its constituent components. Once life dies, or it's not easy to find anymore, it's preserved in some way, there might be biosignatures left. So in this case, I've been following the definition of biosignatures being substances, objects, or patterns that serve as evidence of life. So things like elemental abundances or molecules or objects like microbial mats or preserved microbial mats or fossils, and then patterns such as abundances like spatial abundances or organic homologs, or patterns of stable isotopic abundances between different compounds. So those would all be types of biosignatures that we would like to detect in an in situ astrobiology mission. So all of those included. And then if there aren't biosignatures, there's still a chance that we could detect some of those building blocks, which is the tie that leads one side to the other side over here. Or if there aren't building blocks, we could at least determine if the environment that we're looking in is habitable or not. So these two lines of thought, I always feel like flow opposite to one another, but they have those common parts, like those building blocks, which include things like organic molecules. So organic molecules, carbon-based compounds, things that could also potentially have things like nitrogen or sulfur, sulfur-bearing compounds. It's really thrilling because it gives us information on all the other aspects of the slide. So finding that key component is something that we would like to do in different astrobiology-focused missions, including Mars 2020. And also, this should be clear, but this is a one potential path of a simplified sequence of events that just looks at two different sides of origin of life versus finding things like biosignatures. So I'll go through a quick overview of mission astrobiology, so what we're doing on Mars with the Perseverance rover, then go into that one instrument that I'm working on called SHERLOC. So the Mars 2020 mission has 4 science objectives. The first is geology, so to study the rocks and the landscape at the landing site to reveal that region's history. So we want to understand and characterize the processes that formed and modified the geologic record in the site that we're in, which is Jezero crater, that was selected based on evidence of astrobiologically relevant ancient environment and geologic diversity. So one of the goals of the mission is to explore this area because it had the potential to host and preserve ancient life. So Perseverance will be able to explore that region and answer some of the key questions that we still have. So was Mars warmer? How wet was it? When was it wet? And how hospitable was that to life? So part B is to understand more of the astrobiology side. So whether that region of interest is suitable for life, and then to look for signs of ancient life. So we are going to, and we currently are, performing a bunch of different astrobiologically relevant investigations on the geologic materials and minerals in Jezero crater to determine habitability and then any kinds of signs that life may have been there. So we're looking a lot for minerals that have high biosignature preservation potential to search for potential evidence of past life and using that preservation from things that we've studied on Earth analog environments on Mars. And then objective C is sample caching. So you've probably heard about this sample caching because this is one of the things that makes the Mars 2020 mission stand out in comparison to others. So one of the main aims is to get the most promising samples that represent the geologic diversity and potential any signs of life, and to document the context of those samples thoroughly and to bring them back to Earth potentially in the future. So in this case, what we have is 38 different tubes where we're going to collect rock and regolith, and we've filled some of those so far, which I'll talk about at the end of the presentation, and 5 witness tubes, which capture the environment in which we're collecting all of these cores. So this is what a typical core looks like. So there's the sample, which is inside a titanium tube. It's collected with this drill bit, which has a hole in it, so that's how you can get the core rather than just making a hole into the rock. And each of the tubes will hold about 10 cubic centimeters of material. And then once they're collected, they're stored inside the rover itself, and then eventually it will be probably dropped off at a location so that it can be picked up later by a fetch rover. And then the last of the 4 different scientific objectives of the mission is to test technologies that would help sustain human presence on Mars someday. So some of the instruments that are on the rover are demonstrating in situ resource utilization technologies. So things that could be related to helping humans survive on Mars. So things like creating oxygen or understanding more about how to use propellants in that environment. Those would all be parts of what some of the instruments are doing. And then other things related to this is understanding more about the weather on Mars and how much it varies over the course of a sol or Martian day, and what sort of things we can do in terms of thermal protection, aerodynamic performance, and aerothermal conditions that would affect how we would land and operate on Mars in the future. So this is one of the instruments that's on the rover that's specifically involved in that Objective 4, which is called MOXIE. And so MOXIE is the Mars Oxygen In Situ Resource Utilization Experiment. And so this is a tech demonstration that produces pure oxygen. So this is a quick demonstration of what it's done, and it has operated successfully so far. And so this tech demonstration happened within like the first 2 months that we were on Mars. And so it's one of the many firsts that this mission has had so far. So with that, welcome to Mars. This is a view from Mastcam-Z, which is one of the instruments that's also on the rover, and it was taken on Sol FLAR 15, which was fairly recently, at the local mean solar time of 1221. So this was taken during a sol where we drove a significant amount towards the delta of Jezero crater, which is where we're beginning the next phase of this mission. So this is a series of images from the nav cams that are on, or navigation cameras that are on the rover, and it shows a gust of wind that's sweeping across the Martian plain. And this was taken back on the 117th sol. And I think what it really shows is the area that we're in. So for me, as I'm doing research, I always need to try to ground myself in the environment that I'm thinking in, because some things don't make sense at all if you start to think about Mars in the context of Earth, because of course they're very, very different. And we are trying to pull understanding from Earth into Mars, but questioning the context and the confidence with which we're making any assumptions is something that I'm still learning how to do. So one of my favorite things to do on the mission is to just look at images and look at things like this, like these different movies and Dust Devil movies and things like that, to really get myself in the place of where we're doing the science. So our view of Mars has been steadily changing over the past several decades, with each mission from Viking to Perseverance adding a little bit more information about the planet. And so this is a little bit of the missions that have happened and that are potentially planned. And so since February 18th, 2021, after a 200-ish day journey, in which it traveled over 290 million miles, the rover and the helicopter Ingenuity touched down in Octavia E. Butler landing site in the crater. And so this is a real image that was taken by cameras that are part of the rover's entry, descent, and landing system. You can watch the video, and there's a couple of other pieces of footage that are really interesting on the website. And so this is showing the parachute deployment as imaged by a camera that's on the aeroshell, which is a capsule that's protecting the rover and looking up. And interestingly, the high-rise camera, which is aboard the Mars Reconnaissance Orbiter, also caught us as we were landing during the descent. And so this is the context in which we were landing, which is the ancient river delta, Jezero crater. So after that 7-month sort of cruise, this is where we landed. And the landing site is called Octavia E. Butler, and so it landed on the floor of the crater, perfectly poised to then eventually go towards the delta. And so a little bit more about this crater, which is the field landing site. So this is located at the western edge of a flat plain called Isidis Planitia, which lies just north of the Martian equator. And the crater itself is 28 miles wide, and the landing site is 2,300 miles from where Curiosity landed back in Gale crater. And we believe that Jezero was once flooded with water and was home to that river delta when Mars was wetter back in its past. And so more than 3.5 billion years ago, most likely, those river channels spilled into the crater wall and they created this lake. So previous studies have identified this very diverse set of minerals that includes things like clays and carbonates through orbital imaging. And those are, on Earth, very good preservers of biosignatures and organic molecules. So conceivably, microbial life could have lived in Jezero crater during one of those wet periods in Martian history. And if so, signs of their remains might be found in the lake bed or in the shoreline sediments. So this is just a little bit of where everybody has landed to date. So you can see where Perseverance is in context of all of the other missions that NASA has put onto Mars. And this is a brief summary of just why Jezero crater was selected as the landing site. So it has some of the best preserved ancient lake and delta deposits on Mars. And some of the minerals in particular that we thought we would see, we actually have seen, and they have really great promise, like carbonates, for instance. So this is just a quick picture that I love because it's very pretty of the crater rim. So this is the prominent crater that's in the center of the image. That one is 1 kilometer across. So the height of this is actually pretty high. So it's 2,000 feet high of the rim itself. And so this was the first high resolution color image to be sent back from the hazard cameras, which are the HAZ cams that help navigate to avoid any obstacles that are on the underside of the rover from the day of landing. And to briefly go over the rover in terms of its instruments. So there's 7 main instruments that are on the rover. The first that I mentioned and you saw images from already is Mastcam-Z. So this is an advanced camera system. It's zoomable panoramic cameras that have the panoramic and stereoscopic imaging capability. So it helps assess the mineralogy of the Martian surface and assist with rover operations. So there's usually a lot of different images that you can see from Mastcam-Z that are really, really beautiful on the website. So there's always the raw images being posted from the rover that anybody can see online. The second instrument is MEDA, so that's the Mars Environment Dynamics Analyzer. So it's essentially a little weather station that's on the rover. And it has a set of sensors that provide measurements of temperature, wind speed, direction, pressure, relative humidity, and dust size and shape. Then there's MOXIE, which we already talked about in terms of a tech demonstration. Then Pixel, which is the planetary instrument for X-ray lithochemistry. And so this is an X-ray fluorescence spectrometer with a high-resolution camera called the MCC, which determines fine-scale elemental composition of Martian surface materials. And so this gives a really high-resolution view and detailed detection and analysis of chemical elements than has been done on Mars before. Then next is RIMFAX. So this is a ground-penetrating radar, the radar imager for Mars subsurface experiment, and that provides centimeter-scale resolution of geologic structures that are below the subsurface, so giving us that view underneath the ground. Then there's SuperCam, which is an instrument that does imaging, chemical composition analysis, and mineralogy, and it can detect the presence of some organic compounds in rocks and regolith from a distance. And then last but not least, this is the instrument that I work on, which is called SHERLOC. And SHERLOC stands for Scanning Habitable Environments with Raman Luminescence for Organics and Chemicals. So this is a spectrometer that provides fine-scale imaging, and it uses an ultraviolet laser to determine the mineralogy at a really, really close scale and to detect organic compounds. So this is the first UV Raman spectrometer to fly to the surface of Mars. And it will provide measurements that are very complementary with the other instruments and also with Pixel in particular. So both of us are the proximity instruments that are on that arm there. So now getting to my favorite part. So this is my favorite instrument because I'm on the team. So SHERLOC is mounted on the arm, and it's, as I mentioned, the deep UV resonance Raman and fluorescence spectrometer. So what makes this different than a lot of these Raman instruments that you may have used in labs is a lot of times those use visible nanometers. So those will use like 514 nanometer or something more in the green range excitation. So in this case, what we're doing is using something that's in the deep UV range. So that's 248.6 nanometers. And we're using a spot size that's not at all like confocal Raman microspectroscopy, but it is still pretty small in terms of looking at rocks. So it's under 100 microns. And so this laser is integrated to this auto-focusing scanning optical system, and it's co-bore sighted with an imager called the autofocus context imager. And so that gives very high resolution but grayscale images so that you can align exactly where we're hitting the rock with the laser onto a context image so you can see which grains we're hitting in particular, for instance. And so we're able to get that spatial resolution of about 30 microns with the ACI. And so the real magic of SHERLOC is that it enables non-contact but spatially resolved and very sensitive detection of organics and minerals that are on the surface. So we can operate over a 7 by 7 millimeter area through the use of an internal scanning mirror. And there's we use some of the heritage instrumentation from Mali, which was one that was on the Curiosity rover, and we can do arm placements from 48 millimeters above a natural or abraded, meaning scraped off with a braiding bit surface, without the need for doing any sort of rover arm repositioning. So the other thing that we can do is also image inside those borehole interiors. So imagine you take a sample out of a rock. SHERLOC can use its other camera, so there's the ACI, and then there's another camera called the Watson, to image inside there. And that can be sort of a proxy for what the rock is like inside and direct core analysis as well. So there's those three systems, the spectrometer, which can do Raman and fluorescence spectroscopy, the ACI, which is the one co-bore sighted with a spectrometer, and then there's that other camera that I mentioned. And so this is the one that's the heritage instrument. And so this is a near field to infinity imaging system called Watson. And Watson, of course, is another acronym related to SHERLOC, which is the Wide Angle Topographic Sensor for Operations and Engineering. And so this is based on the Mars Science Lab Mars Hand Lens Imager, and it works well with the existing electronics within SHERLOC, and it provides this larger view. So instead of being very close to the surface, you can actually focus at several different standoffs from a rock, and so you can get larger context. So if you imagine all the cameras, I think there's 27 cameras on this rover, we can go all the way from that really, really far out view that Mastcam can provide, and it can zoom in, to then something like SuperCam, which has its own set of cameras. And then we can go to Pixel, which has that context imager, the same way SHERLOC does, and we have Watson to bridge the gap between that really micro context and the larger scale. And so across all of those, you can imagine just zooming in, actually even from an orbital level. Imagine you're going from high rise, so those first pictures that I showed of the delta, you're going from that level all the way down to just a piece, a 7mm piece of a rock. We're able to get all of that context through the different cameras that are available on this mission. So the goals of this instrument, just briefly, are to assess past aqueous history, to detect the presence and preservation of potential biosignatures, and to support the selection of return samples. So that's always one of the questions is there's a lot of options of where to core and pick up a sample to then try to bring back to Earth. How do you decide which one is of most promise? So we try to use the proximity sites instruments, meaning SHERLOC and Pixel, to make those determinations. So we can detect a wide range of different minerals and also different types of organics that could be preserved within them and on the surface, and correlate those back to textural features. So a little bit more about deep UV Raman and fluorescence. So the fluorescence, native fluorescence is sensitive to condensed carbon and aromatic organics, which would enable the detection of like at or below 1 ppm at less than 100 micron spatial scales. So we can detect especially aromatic organic compounds at very high sensitivities. And in addition, we can classify different minerals that are detected, especially ones that are relevant to aqueous chemistry, with grain sizes that are about 30 microns or lower. And so the use of those two different spectral phenomena, so the native fluorescence and pre-resonance or resonance Raman scattering, provides a really powerful analysis that hasn't been done before on Mars. So the organics that fluoresce absorb incident photons and re-emit at a higher wavelength. And the interesting thing about using 248 nanometer excitation is that you can separate the fluorescence region from the Raman region. And so you have a fluorescence-free region that exists from 250 to 270 nanometers or so. This is where all the Raman scattering is going to occur. And we won't be flooded out basically by seeing fluorescent signal. And so that in that area is where the fingerprint regions for a lot of the organics are. So we can see aromatic organics fairly clearly if they're present. And the other thing is that by using this particular deep UV instrument, we're able to enhance some of the signal from organic and mineral vibrational bonds because we can couple the incident photon energy to the vibrational energy. So we get very high sensitivity and high resolution measurements with low backgrounds, and we don't need to use very high intensity lasers. So we don't think that we are damaging or modifying organics too much. And we shouldn't be introducing any sorts of reactions, but of course we're still reevaluating as we're doing work on the surface. So it's a very promising technique, and this is some examples of what signals look like after some processing to make very pretty spectra. So we can detect things like nucleic acids, amino acids, polycyclic aromatics and hydrocarbons, and then oxidized organics as well. And so these are all, of course, very relevant to detections of things like biosignatures, but also are similar to, this would allow us to detect the things that, say, the SAM instrument has detected on Curiosity and Gale Crater. So they've seen a diversity of different organics, including things like chlorobenzene and S-bearing organics and N-bearing organics. So we'll be able to see those same things as well. And we'd also be able to see some of the condensed carbon, macromolecular carbon, and PSAS that are seen in Martian meteorites. So we've vetted this instrument on the ground, and we have a few different analog instruments that are on the ground that I operate at JPL, and there's a few others at other NASA centers. So we can create reference spectra to compare against what we're seeing on Mars. So basically what we typically do is we have a library that we currently have and we're still building up more and more, where we find minerals that are relevant, so maybe a type of carbonate, and then we can scan that with our two analog instruments at JPL to understand what that spectrum would be expected to look like. And so then when we get data down from scanning an actual target, we can just overlay one on the other, or try to subtract it out to see what's there and what's not there within the spectrum, because of course we're not hitting any of these pure samples. That's, I think, one of the big challenges in terms of extrapolating from the reference spectra we have to what we're seeing on Mars is Mars rocks will have mixes of a lot of different stuff in there. So that's why we use some field analog samples, so you can understand what things would look like in context. You have mixed organics and minerals and contamination and all this other stuff. And then you have pristine samples to compare against too. So between those, we're trying to get a good understanding on Earth to support science return and science investigation on the surface. So one of the things that I've been particularly interested in is how do you get these two cameras that we have on SHERLOC to talk to one another? And so imagine we have three different pieces of information, right? We have textural information, we have the fluorescence, we have the Raman. And so those are the pieces of information that we're trying to put together into one spot. And the textual information breaks down into the actual, like imagine you're seeing high resolution of all the grains in grayscale, and then you're seeing color information. So you can tell that there's maybe a large crystal that looks this particular configuration and it's in context of all these other minerals, but you have a separate image that has all of the color telling you that crystal is actually white and the ones around it are brown and it looks like there's a rim around that crystal and things like that. So how do you take those pieces of information and put them together effectively so you can get texture, color, and spectral information all from one set of data and all from one image ideally? So this was one of the first challenges that I started to look at during my postdoc. So I mentioned that the ACI, the context imager, is co-boresighted to the spectrometer. But the other camera, that Watson, the one that is heritage from the Mali instrument, that one is not co-boresighted. But we are imaging the same area. So imagine you're approaching a rock. You've imaged it with different cameras. But how do you get all of those together to register and overlay the images perfectly? So this is a sequence that I have been developing to go from all those separate images into composite images that are secondary products that will give you more pieces of information at once, and that you could eventually use to do automated analysis. So automated image analysis is something that I'm particularly keen on, both for creating composite images, but then also analyzing it to maybe do things like identifying specific grains, understanding boundaries and contours, outlining them, quantifying the sizes of grains and their shapes, as well as their colors. So this is a quick run through. I'll just walk through it. But basically there's 6 different steps that we'd like to do. So first is acquiring images. So acquire them on Mars and then we bring them back down. When we get them back down, they go through their own processing pipeline in an automated way. And then we can download them as like PNG images or things like that. Then the first step is to focus merge. So a lot of the time we can take images at slightly different distances from a surface. And because the surface is not flat, you need to focus all of those images together so you can get one composite where everything looks like it's actually in focus. So that's a focus merge. You can crop to remove any artifacts on the side. And then the next thing is to do flat field correction. So flat field correction basically fixes uneven illumination in images. So this is often something that we see because imagine we have a camera with some LEDs in the middle. That middle part is going to be the brightest. The outside parts are not quite as bright. So we're able to correct for that by doing images of just the sky. We just image the sky, so those are our sky flat images, and those can be used to basically subtract out of the image that you actually take, so you can get rid of all of those darker areas on the side. And then you can also remove some geometric distortions and remove foreign object debris that might have shown up in. Then the next step is to do key point matching. So there's several different algorithms that are available through packages like OpenCV with Python that allow you to determine where these points are, anchor points essentially across images that you can use to register them and overlay into one spot. So we identify those and then overlay them and then do color blending. So identifying, matching, and color blending then gets you to the point where you have a composite image. And after that, you can start to do things like sharpening or cropping or adding scale bars and different things like that. So all of the other things you would want for a secondary product. And then because that resulting colorized ACI image, essentially, because it has color from the Watson and it has the texture and overall image size of the ACI, that can be used to then overlay the laser scan map. So every place that we've hit directly with SHERLOC, you can hit with that map. You can mark with the map. And so then you have that scan map on top of a colorized ACI, and that tells you not just we hit 100 different places on this rock, but we hit 3 points on a white grain that's in the top right side of this. And we got signals that look like hydrated sulfate from there. So all of a sudden you have a bunch of information that is much more akin to what you would understand in lab when you're able to look at a sample and understand where you're hitting it. And all of those pieces of context are very helpful in doing geological interpretation, but also if we detect organics, understanding where those are and potentially organic mineral interactions. And so this is sort of the stage that I'm at right now, doing these automated detections. So yeah, this is just another little flow of everything that's there. And so this is an example. So this is the original ACI image that we had for a target called Bellegarde. And it's a really beautiful one. You can see so much texture and information there already. So there's some things like this grain on the right side that I would be curious to understand, is that really white or are there other colors that are around there? And that's the information that I can get from a Watson image. And then the other things are there's some glassy pieces here. And I'll show you kind of what the artifact looks like of glassy pieces. But this is all important in doing interpretation in a geologic or mineralogical way of what's on the surface. So this is a flat field corrected image. So you can kind of go back and forth to see those darker regions on the side have now become sort of grayed out. Of course, there's still that fuzziness on the side because where there isn't enough light, there is no textural information because we never collected that information onto the detector. And this is one of the early attempts at colorization. So you can see that the ACI image has basically stayed the same. The only thing that's been added on are those pieces of color information. And so when I saw this image, I was like, okay, this is really interesting now because it looks like a lot of these white crystals or these white features are now surrounded by this dark brown. And then you can also see pockets of smaller, darker material within there. And so now when we do a laser overlay onto there, you can see whether we hit those white grains, whether we hit the rims that are on the outside of it, and then whether we got those dark spots too. And so for this image, I'm trying to remember right, we were able to see detections of sulfate on a lot of those white pieces and some amount of hydration with that. And then on some of the brown areas that correlated to a carbonate detection. So this was a really interesting sample and a good first case of showing what is the power of SHERLOC in terms of its 3 different subsystems and all the information you can get from 2 types of spectroscopy and 2 types of imaging. So now going through mapping the rocks on the crater floor. So we'll see how far I get in terms of time. So the first big campaign that we did was the crater floor science campaign. So this is going from the landing site in Octavia E. Butler to South Seta, which is one of the lower and more underlying regions that's within the crater. And so this is the crater floor, and these are likely the oldest rocks that we would look at in Jezero crater, and they can tell us about the history before the delta emerged. So this is a really typical view of what the crater floor looked like. And so this was the traverse as it was planned, so landing up at the top, and then going all the way down around the rim. So the area that's in here, in that sort of triangle, that's Seta, and the rest of it is called Maz. And so we went down through Maz and around the rim, and then went down into Seta. And so we did samples both with our different instruments and also collecting cores in each of those areas. And so this is actually the path that we followed. So you can see we tried to trace our steps pretty closely, but we did make some deviations there. And so this is a little bit more about the different crater floor units. So initially when they were mapped with orbital imaging, the unit that I was mentioning called MAS, that was called the crater floor fractured rough unit. And so that's thought to be younger because it's overlying. And then on the left side, you can see in green, that's where SETA is. And so Bellegarde, the image that I showed you that I did the colorized ACI on, that was in the MAS unit, so the crater floor fractured rough unit. And so this just goes through a little bit of the different rocks that we've seen, or the members. So this is the Natani member, which was a low relief polygon. And so we saw this characterized by rounded edges. There was a crumbly surface texture, and we thought there was weathering of granule-sized fragments. There were not that many internal structures, and it corresponded with polygons that were seen in orbiter images. And then there's the Chesh member. So these were the massive high relief rocks. So anytime you see these like NavCam or MassCam images, I'm always stunned by what geologists see in all of this, because of course the team is very, very interdisciplinary. For me, this is some of the first times that I'm really understanding why geologists see the world the way they do. So why do they see so many different things in rocks where I would normally have thought, oh, it's just a rock? No, it actually means so much more than that. So I'm getting a great appreciation for that, and I hope people are also getting a great appreciation for image processing and why that's so interesting. So these were some of the very massive blocks that we saw, and there was some candidates for layering or parting within it, but there wasn't abundant layering that we saw within these rocks or evidence for specific sedimentary structures. So we had a Rubion, which was our first sample attempt. And then the first abrasion that we did on Mars was called Guillaume. So there's two different types of samples that we look at. So there's natural targets, which is ones that we don't scrape off the surface at all. We just image the rock and analyze it directly as is. And then there's other ones where we do abrasion. So we have a couple of different types of drill bits on the rover. One is the coring bit that I mentioned that has the hole in it that you can pick up a sample. Another one is an abrasion bit that just scrapes off those surface layers that would have been very affected by any sort of surface conditions, including things like high UV flux. So things like organics probably would have been obliterated there. And then we go a little bit deeper into the rock by doing the abrasion. So hopefully more things will be preserved in there. Though of course things like ionizing radiation would still have an effect, Actually, I'm not even sure how far down ionizing radiation will have an effect, but definitely still in the layers that we're in. So this is an example of some of the multi-instrument analysis that we can do. So several of the different instruments that I mentioned, so the two proximity ones, SHERLOC and Pixel, and then things like SuperCam, can all image the same area, so we can get several different types of information all at once. So on the right side here, this is a colorized ACI inset of the Guillaume target. And so you can see all the different techniques that were used. So Watson imaging, SHERLOC for microimaging and mineralogy, Pixel for elemental chemistry, and then SuperCam for a couple of different things. So here we detected some salts, iron oxides, silicates, apatite, and considered it to be a mafic composition. And now this was a drill attempt that happened, but we weren't able to collect the sample here, I believe. And so continuing on, we went down to our 2B ridge. And so this is what that ridge looked like, so some NavCam images. And you can see all of the detail and structure that's on there. So NavCam versus MassCam show very complementary types of images here. And this was one of the places that we were at for quite a while doing analysis, which was Citadel. And Rochette is one of the rocks that then we started to analyze next. So the next abrasion patch that we did was on Rochette, and that was Bellegarde. And so that's the one that you've already actually gotten a little bit of a look at. So this is a Watson image of it. And so you can see there's the abrasion patch that the 45 millimeter diameter. And it's a pretty much perfect circle. And so we try to target regions within there that we think look interesting based on Watson images for the proximity science observations. And so these are comparing the two different targets that we had looked at first. And one of the tricky things that applies to any of the image processing and image interpretation is the lighting conditions, because we're not always able to image with the exact same light, of course, because seasons are changing there, and also the times we're imaging are different. So when you say something is reddish brown, it might look reddish brown in some images and much less so in others. So one of the things we've tried to do with Watson more recently is image under several different illumination conditions, so you can understand more and not bias yourself based on just one color interpretation that you might have seen. So this is what you had already seen for Bellegarde, the ACI image. And then this is a SuperCam summary of it. So they found minerals that were consistent with igneous rock interpretations and presence of salts. And so you can see how that's complementary with SHERLOC's summary of Bellegarde. So we found angular elongated crystals rather than the rounded ones. So that's consistent with igneous rock. We found salt as well with our spectroscopy. So we saw some calcium sulfate and calcium phosphate. And that area that we were imaging was 6 millimeters per side. So the entire scan actually goes up to 7 millimeters, but this shows some of the places that we were able to do mineral identification. And then once again, we have another complementary technique, which is pixel. And so through pixel, we were able to also look at calcium sulfates. They found over 20 different elements there. And we're able to do this correlation where we felt very confident in the detections that we were seeing with SHERLOC. And then we had a drill attempt through here. And so you can see the abrasion patch and then the drill. And one of the interesting things I find about this is just how fast that abrasion patch gets covered by drill tailings and also just dust that's on the surface. And this is what it looks like when you succeed in actually picking up a core. So this is the Mondenier core that was picked up inside its cache. And then this was the first sample that was sealed. So that was sealed into 266. And so getting that confirmation image was very comforting, I think, for everybody on the team. And so in most cases, we're trying to do paired sampling. So we pick up 2 samples from the same rock so we can drop half somewhere and then also have some options for when we do Mars sample return. And so then the diversity of igneous minerals in the Jezero crater floor is something that we've been learning more about. So as we go through and do all the different analyses and sampling, so we're able to get more information to get a more global understanding of what's happening in this region of the crater floor and then potentially extrapolate beyond that. So in terms of SHERLOC's activities so far, we've looked at 3 natural sites and 7 abraded ones. And now this campaign has essentially wrapped up and now we're moving towards the delta as the next step. So we're expecting the delta will be very, very exciting. There's actually a lot of publications that some of you are probably very familiar with about why we're so interested in it. We think that it's one of the highest targets for potential biosignature preservation because we're expecting to see clays and carbonates there that should be able to preserve things like organics for a very long period of time. And I think, actually, how much more time do I have?
You have some time. I think you have a good 5. We end at noon here, but of course, if we want to open it for questions, you have like 5 to 8 minutes, I think.
Okay. Actually, maybe I'll open it for questions because I know I've just been talking straight at you for like 45 minutes, so feel free to start asking questions.
Great. Well, thank you for that talk. It was great. Let me stop the recording and then, yeah, we can transition on to doing questions.